What do you think the most fundamental thing is? In the world, in the planet, in the universe, what's the most fundamental thing that there is? What do we all need? We need energy. Energy. Without energy, we wouldn't have a solar system. We wouldn't have anything. Nothing. There'd be nothing here. There'd be no sun, nothing. We have no rain. That's what we're doing. We're following nature. We're doing what we should be doing. This is a factory. We want to get away from the waste industry image. This is a clean factory. That's what we're trying to achieve. That's what we're striving for. The mark of a good engineer is imagination. That's what makes a good engineer. It's not science. It's not science. Science is straightforward stuff. There are rules in science. Lots of rules that you can follow. You know, the book. If you read enough and you can remember things, you can be it. You need to be creative. That's the art of engineering, is creation. There's a lot of creation gone into this planet. Hello, my name's Tom Wilson, Chief Engineer and Designer of the Wilson System. We're here on site in Limerick at the RE3 plant, and we're about to take you a short journey where we'll describe each of the various components that make up the Wilson System. We're now in one of two reception areas on the site here in Limerick. This area is used to receive waste from its transport. It's tipped from the transport onto a flat floor. The waste forms a natural, very shallow angle of repose whereby items can be easily seen and removed. Once the unwanted items are removed, the waste is shoved. It never leaves the floor. A series of elevators carry the waste up to a second series of elevators, and the central control system having made a decision on which autoclave that the waste is going to be transported into. We'll now move on to the next stage of the process. We've just been in the reception area where we've seen waste loaded onto the conveyor system. The waste is delivered to this area, and this area is the autoclave area. There are two autoclaves. Each of the autoclaves rotates, and each autoclave is charged with steam and in a controlled environment. The steam is the element which brings about the necessary conversion of the biomass content of the waste into the fibrous product that you'll see later. Other components within the waste, for instance aluminium cans, are stripped of lacquer both internally and externally. The cans are flattened due to the dynamic forces within the autoclave. Tin cans are stripped of labels. If there were any beans in the can, the beans are out. The beans are fibrous material, and the beans are also in the fibre. Plastics, because of the temperature in the autoclave, try to revert to their natural spherical shape and shrink duly. Various other materials, rags, etc., remain within the autoclave and are broken up into smaller components. Following completion of the process, steam is discharged from the autoclave under the command of a control system, and the steam that's discharged, in other words the exhaust steam, is condensed and reused within the boiler as boiler feed water. Therefore, we don't waste any of the natural resources that we have here in this plant. Further to that, steam from one autoclave, once its cycle is complete, can be discharged to the next autoclave, saving steam and saving, of course, energy in a different way. We're now going to go to a more interesting area. Well, it is for me. We're going to go to the rear of the autoclave where you'll see the pipework distribution system. If you want to come round here and follow me this way. Well, here we are now, as promised. We see these exciting pipes. These pipes are designed to transport steam into the autoclave and take exhaust steam from the autoclave to be condensed and used as boiler feed water, as previously talked about. There's a third use of the pipes, and that is to take steam from an autoclave that's pressurised and almost finished its cycle to charge into an autoclave that's depressurised and ready to start its cycle, thereby saving steam and valuable energy. We've looked at some of the major components within the plant, but what we haven't looked at and what we can't look at is the steam. The quality of the steam is extremely important. quality of steam is usually measured by something called its dryness fraction, which measures the amount of water entrained within the steam. We generate steam conventionally in a boiler on an average rate, and we take that steam to the steam accumulator. The steam accumulator is an extremely important part of the plant. It's a simple piece of equipment. It's a physical piece of equipment that works. It uses simple physics to generate steam. In other words, the steam that's condensed in the body of water within the steam accumulator reboils of its own internal energy when there's a pressure drop within the steam accumulator. That pressure drop is brought about by the fact that a control valve under the command of the control system is opened and is discharging steam into the duty autoclave. There is enough steam in the steam accumulator for one complete cycle, thereby providing extreme security to the system. In other words, if a boiler fails, there's enough steam on tap ready to put into the process. The steam quality is extremely high because the water in the steam accumulator is extremely high. Remember, it's condensate. It's pure water from which steam is being generated. When steam discharges from an autoclave, it also carries non-condensable gases. And because they're non-condensable, sometimes in some processes these gases are emitted to atmosphere, and it's that smells. Within this system we contain that gas, or that non-condensable gas, within a sealed system. We then take the odorous component to an odour abatement system. The odour abatement system again is conventional. It's an activated carbon filtration system with impregnated copper. That system takes out all odour and discharges clean air to atmosphere with no visible emission. Here behind me and before me there are two steam boilers. Each steam boiler is of conventional design and is designed to carry the average demand of the plant. The boilers act as duty standby, thereby providing 100% redundancy to the system. In other words, if there is a breakdown on one boiler, we have another to take the load. The boilers have duplex pumps. That means there are 2 pumps per boiler, the pump being the fastest moving part in the boiler in general, and therefore the component that could fail. The other virtues of these boilers are that we have full heat recovery. We have a feed water economiser. A feed water economiser takes waste heat from the flue gases and transfers it to the incoming water, thereby making the whole system more efficient and saving fuel. Other energy saving devices are incorporated with each of the boilers. Variable speed drive on all the motors, saving energy and providing extremely precise control. We have modern level controls that are state of the art, non-moving components. In short, the boilers, whilst being standard components, have been designed specifically for this system, bearing in mind the energy requirements and the tight control that we require in our system. High quality feed water is essential in a plant such as this. The quality of the water determines the performance of the boiler. The higher the contaminant condition of the boiler, the more water you need to take from the boiler. And remember, the water in the boilers reach saturation temperature, and valuable fuel's being used to do this. So the cleaner the water, in other words, the lower the contaminant level, the less water we have to waste and the less energy we need to waste. We also take in the water that needs to be made up to form the full component of boiler feed water. We don't make the whole component from condensed steam. We need to take some water from the mains supply, and even the water from the mains supply needs cleaning. We take that water through a softening process, and then it follows the same route as the previously condensed steam and is cleaned to the same level, and thereby reducing contaminant level to virtually zero. We're now in the area where separation takes place of the materials that have been processed within the autoclaving system. Here we have magnets that take out ferrous metals, we have an eddy current separator that takes out the non-ferrous, we have a density separation method that takes refined fibre to storage. What you see here is conventional plant. This plant's used extensively throughout all the waste industry. Here I am now standing in the area where separated aluminium is stored. The value of the aluminium depends on its cleanliness, and here we see clean aluminium stored. In the next bay there are ferrous metals stored. There is a bay for the various types of plastics, and plastics can be segregated into the various different types. And further downstream of here we'll see the major component of the largest component within the waste stream, the cellulose fibre. Well, here we are now in the area where the fibre is stored. This is the exciting component that we've described all the way up, and at last we're seeing it. This could be, well, in its previous life was a banana, it could have been an apple, it's a newspaper, it's cardboard, it's any natural component, and the natural component being described as biomass. And this is pure to within the limits of any legislation to use as a clean biomass fuel. For me, this is a personal achievement. It's a culmination of many, many years of experience within the steam business. Steam in the past has been thought of as an old relic. It's not. This is a new industry. This is the same steam as used in the Industrial Revolution, but this steam is now being used in the waste revolution. Here we have a new industry, steam driven. This is the end product of the Wilson system. A new industry, a new future, and I hope that you'll be a part of that future.